Okay, last week our goal was continuity, and the intermediate value theorem is a big theorem in continuity, so we did some topology stuff, some stuff with sets that gave us connectedness so that we could talk about the intermediate value theorem. This week our goal is differentiation, and one of the big things with differentiation is that we can maximize and minimize functions by finding where the derivative is 0. So to do that, we have to do some set things too, and we're going to have to talk about compactness of sets. So compact means everything's kind of close together, even finite in some sense. So let's get together a definition of compactness. We have to define an open cover first, so our first definition is an open cover. So let E be a subset of X, a metric space. Then a collection of open sets, say O alpha, where alpha is in some index set. It can be a finite collection, it can be an infinite collection, it can be uncountable, it could be countable, just a huge collection of open sets, or small collection. We say this is an open cover so it's an open cover of E. Oh, these guys belong to, each one of these is in X. Is an open cover of E if the union of all of them covers E. So E is contained in their union. Then it's an open cover of E. So for example, let's draw E. An example of an open cover would be, maybe this is O alpha 1, O alpha 2, O alpha 3, O alpha 4, O alpha 5, and so on. I've got open sets. Each of these open sets, and maybe one big one at the end. Okay, each of these open sets is contained in E. And if I fill in all these little holes that I missed, I think I've got all of the spots now. Each of these open sets is in X, and they cover E, so this is an open cover of E. Alright, now we can define compact. A subset E of X is compact if every open cover of E has a finite subcover. Okay, so what does that mean? Well, that open set, the collection of open sets could have been absolutely huge, right? I could actually have like an open set for every point in E if I wanted to. I can draw a neighborhood around every one of them, and that could be an open cover. Well, for a set to be compact, I really only need to pick out a finite number of them. Maybe 10, maybe a trillion, maybe a googolplex of them. But just a finite number of them would work. Okay, that's what it means to be compact. So it takes like this infinite thing and it makes it finite, which means we can usually actually find maximums and minimums and such like that. So let's prove a couple theorems first before we start talking about maxes and mins. Maxes and mins will probably happen in another video today. So let's first prove a little theorem. If E, a subset of X, is compact, then E is closed. Okay, so I'm going to have to use my definition of compact to get something closed. Compact has to deal with all kinds of open sets. So I'm probably going to look at looking at E complement and showing that it's open, because we like working with open things. So that's going to be how our proof goes. Okay. So let P be in E complement, so outside of E. And what we're going to do here, so here's X, here's E, and here's this point P. For each point Q over here, I'm going to make a open circle, open neighborhood around Q, and this radius is going to be half of the distance. Right? So it never gets, this circle never gets really that close to P. And since I'm going to do this for every Q and E, that's going to be our open set. Okay, I'm going to do this for every point, and I'm going to get an open cover over here, and that open cover is going to end up to be finite. So I can draw a small circle here, which avoids all of those finite circles on that side, on the Q side. Alright, so let's step through this. Let RPQ equal the distance from P to Q divided by 2 for each Q in Q. Actually, since P is fixed, let's just call this R sub Q. So it's half the distance from P to Q. Set, we're going to take V, let's call them O sub Q. These are going to be our open sets in the cover. And it's going to be the neighborhood of radius Q about Q. Then the collection O sub Q for Q and E is an open cover of E. Every point in E is in the union of these, because every point in E has an open set in this collection that contains it for sure, right? The one that has it at its center is contained in the collection. So this is an open cover. Since E is assumed compact, there is a finite subcover, say OQ1 through OQN. Let R P equal the minimum of RQI from I equals 1 to n. So the minimum of the radiuses of these neighborhoods, right? Then the neighborhood of radius P around P intersect the open set of radius QI is equal to the empty set for each I. Okay, so let's draw the picture showing that for sure. So here's P, here's E. So I've got a finite number of points in here. Let's just say that there's 4 of them. And each of these points, let's call it Q1, Q2, Q3, and Q4. This guy's P. Has an open circle that the radius is halfway to P. So I've got this open circle here around Q1. I've got a slightly bigger open circle because Q2 is farther away from P. So slightly bigger circle around Q2. About the same size around Q3. And a slightly smaller one around Q4. So I've got these 4 dotted circles around here that cover all of E by compactness. And I've got this other circle now that's at most half the distance to the closest one of these, right? So like the closest one, it looks like it's down here. So I'm going to draw this circle that gets really close to the Q4 circle, but not quite. And this is our P. Okay. So this neighborhood, it's the smallest of these distances divided by 2, so it's not going to hit any of these circles. All right. Our conclusion then is, so in our P of P is an open neighborhood of P completely contained in E complement. E itself is inside all of these orange circles. The purple circle doesn't overlap with any of the orange circles. And since E is inside the orange circles, the purple circle can't overlap with E at all. Therefore, the purple circle is completely contained in E complement, and this makes P an interior point of E complement. Since P was arbitrarily chosen to be in the complement of E, every point of E complement is an interior point. Every point of E complement is an interior point. So E complement is open, making E closed. Okay. So compact sets are closed. That's what this says. Okay, let's do one more quick proof of a theorem about compact sets, and then we'll get some more in the next video. So this is another theorem. A closed subset of a compact set is closed. For example, say E subset of K subset of X. If this guy is compact, and this guy is closed, that implies E is compact. Okay, so let's prove this. This one's not too bad, it's pretty quick. We have to do the finite subcover thing again. So I need a open cover of E, and I need to find a finite subcover of E. So let O alpha, I'm not going to say what the index set is. Alpha can range between a whole bunch of different alphas. So let this be an open cover of E. We need to find a finite subcover. Well, we're going to go up to K and then come back down. So then if I take O alpha and I add the set E complement, since E was closed, E complement is open, then this collection is an open cover of K, right? Because E complement is everything that wasn't in this stuff, and K might or might not be in that stuff, but E complement covers everything else. And E complement is open, so together these two collections of sets give me an open cover of K. There's a finite subcover. Say O alpha 1 union O alpha 2 union ... union O alpha n, and then maybe we union E complement 2, maybe not, we don't know, is a finite subcover of K. Either way, even if we do include this guy or not, this gives us O alpha 1 union O alpha n is a finite subcover of E. E is contained in K, and so E has to be contained in this union up above, right? This first union. E is contained in the first union. This is our second union. This last set here doesn't affect coverage of E at all because it doesn't have anything contained in E in it. So if E is going to be covered by the first union, E had to have been covered by these first few things. Alright, so E is covered by these guys too. That gives us a finite subcover of E, which makes E compact. Okay. That finishes that proof. Compact is going to be pretty powerful for us because when I can take something infinite and make it finite, I can usually pick out, okay, which one's the maximum thing or which one's the minimum thing. Remember in our proof that showed that compact sets are closed, we actually took an infinite number of radiuses, and I don't know, maybe there's a supremum for the radiuses, but those could have been unbounded. They could have been infinitely close to 0. But when I picked out a finite number of them, I could actually pick a minimum or a maximum of those finite number of things. Okay, that's going to be really useful for us when we're trying to maximize and minimize things.